Step away, please. Thank you. So, today we are going to be... Oh, shoot. Actually, I think I've got my days mixed up. I don't think you need a calculator today. Oh, my bad. You might want it for a couple things, but it's not going to be like a calculator-heavy day. I got mixed up on what we're doing today. I was thinking about what we're doing tomorrow. Okay. Well, calculator will still be good on something. So, today we're getting into what essentially is going to be our last day that it's going to feel a little bit more like an English class. But it's going to start to mix itself, feeling a little more mathy at the same time. So one of the things that I've talked about over the last couple days is when it comes to doing math, generally speaking, oftentimes we are given something and we need to manipulate that something into kind of gathering correct information out of it. And that's where we're going into. We're going to be shifting soon into trying to do what are known as proofs. And in order to do a proof, you have to have legitimate proof to say something is true. In order to do that, you have to use sound reasoning. Reasoning comes in two different forms. One thing that people often do is they look at patterns and they make what's known as a conjecture. And a conjecture is an unproven statement that is based on what you're observing and patterns. Now, conjectures, they are great in order to kind of make sense of what's going on. The problem, though, with conjectures is that conjectures sometimes are wrong. Sometimes you make a conjecture and you've made a mistake about what it is that you're talking about. So, because of that, we have to be careful when we're trying to talk about something being proven. We have to make sure that we've got a solid foundation. So, making these conjectures is working with a form of reasoning that is known as inductive reasoning. And in inductive reasoning, you're taking information in order to come up with this conjecture, with this conclusion of what's happening. Inductive reasoning is based on patterns in specific situations and where you make kind of a logical argument. So, we are going to be making some conjectures based on patterns that we're seeing. So we're going to describe the pattern. That description of the pattern is the conjecture. And then we're going to use that pattern to continue and find the next couple iterations or the next couple terms that would go in that pattern. So I have the pattern SRQP ... What's the pattern? You're getting closer.
Wrong way.
We're going the wrong way, though. So, Cam's thinking alphabet. Think about that part of the alphabet. That part of the alphabet goes, well, let's start back at L. L, M, N, O, P, Q, R, S.
O, N. N, O. It's just backwards.
Thank you. So, the conjecture, the description of the pattern is alphabet backwards. Specifically starting at S. If you didn't write the starting at S, that's okay. Okay, and if I've got L, M, N, O, P, What would be the next two? O, then N.
That's it, sorry. I don't think the answer is oxygen. You said that.
I know, and then I looked at the number 2 and I wrote a 2. It never happened. You saw nothing. I don't know if I can come back from that one, but we're gonna try. Yep. Don't get me wrong, I make mistakes. A lot. It's not typically mixing up what an N and a 2 look like.
You just were thinking about oxygen.
Yeah, it's totally about the oxygen. Okay, 1, 2, 4, 8, 16, 32. Yes, it is times by 2. Or multiply by 2. If we write the more mathy version. I don't know why I'm going for the more mathy version when right now I don't know the difference between letters and numbers, but we're gonna try anyway. What comes after 32? Oh, I heard 64. And after 64?
I don't know. 128.
128, if only we had calculators. Okay. This one comes in the picture form. It goes like that, and then that, and then that, and what's happening?
It's adding one more than the last each time. No, it's
It's adding.
multiply by 3. Oh, no, yeah.
Okay.
Oh, it's multiplying.
In all technicality, the number of little circles there is multiplying by 3. But is that going to keep going? Like, what would you tell me the next picture is going to look like? A circle followed by 2 circles followed by 3 circles. So what we have followed by how many circles? 1, 2, 3, 4. Generally, we'd be thinking 4 would come next, right? That's what the pattern appears to be doing. How many circles are there? 10? If we said multiplying by 3 times 3 times 3 is, this times 3, 10? That was 6. 6 times 3.
Wait, isn't it just like you're adding one more every single time, but like, so like how that one's at 3, then the next one, you keep 3 and then you add 3, but then like the next one, basically, I don't know how to explain it, but I understand it. Every single one you start adding 4. So you don't add the same one every time, but you just plus another one that you're adding, but you're already still adding what you added last time. Right?
This what you're seeing?
Like how we added 3, but then next time instead of adding 3, we add 4, and then the next one we add 5. And then
Next one, we're going to add 5 of them to it. Sometimes the conjecture is not as easy to see. The true conjecture is not as easy to see until you continue on with the pattern, especially visually. So, sometimes you might want to start with what's the next one in the pattern? What's the next one in the pattern? Because that's one of the things it asks, is it asks for 2 more items in the pattern. But it also wants you to describe the pattern, give that conjecture. Now that multiply by 3, that was technically not accurate from here to here even. But sometimes seeing a little bit more can help, but sometimes the visual ones are harder to explain in the first place. I would describe this as add the number 1 higher than last time. Now, generally speaking, if the patterns are straightforward enough, inductive reasoning is beautiful to tell us what's going on in a situation. The problem is with inductive reasoning, you're making assumptions that patterns continue. And as we're getting into and starting to do proofs, as I mentioned, we're going to be doing proofs in this chapter, you cannot use inductive reasoning. You cannot use patterns as proof, because by that situation, you can end yourself up in trouble. For example, if I have a student who's late 3 days in a row, can I write them up for being late 5 times in a week if they've only been late 3 times so far? No. That's where using patterns can become a problem. If you use patterns and assume that that pattern's going to continue perfectly, you can make false assumptions. Maybe the person was just having a hard time the first 3 days, and then they show up early even the next 2 days. So, patterns are great, but they're not perfect. That's where our second form of proof, or our second form of reasoning comes in, and this is the type of reasoning that you can use to prove things. It's known as deductive reasoning. Deductive reasoning uses facts. Deductive reasoning would require me waiting till the end of the week to see how many times that student is tardy before I can say they're tardy 5 times. So it uses facts, definition, and laws of logic, technically. Now, facts and definitions, generally, we're good on those. Something is a fact, we know we can use it. Something is a definition, we know we can use it. Let's talk about our laws of logic. Now, there are 2 main laws of logic. One is known as the law of detachment, and the other one is known as the law of syllogism. Yes, not the easiest word to say. Laws of detachment and laws of syllogism work with those if-then statements. The law of detachment, it has this situation where it says if P, then Q. In other words, it starts with a traditional conditional statement where P and Q are just placeholders for other things. And it tells you this is true. It follows it up with saying P is true. Follows it up with saying we know P. From there, you are able to make a conclusion. Using this law of detachment that states, if P is true, we know Q is true. Well, we know P is true, and therefore we conclude Q has to be true. This type of logic, this law of detachment, essentially is the idea of me being able to say things like, if it is night, then the sky is dark. It's night. We can then assume that that means the sky is dark because of that original if-then statement. The law of syllogism is a little bit more complex. It still has 2 statements to begin, but both of them are conditional statements. It says if P is true specifically, then Q is true. But it follows it up with another if-then that says if Q is true, then R must also be true. from there we can make the conclusion that states if we determine that P is true, then by the fact that P makes Q true, and if Q is true, R is true, we're able to say we then know that R must also be true. Where R is also a placeholder, kind of like P and Q, where it stands for other things. It's kind of the idea of if it is night, then the sky is dark. If the sky is dark, then people turn on lights. Well, since it's night, that means people probably turn on some lights. That's how the law of syllogism works. So one of the things that you're going to be asked to do is be able to read some sentences and determine if you can make a logical conclusion. The way that you can make a logical conclusion is using one of these two laws. So you have to be able to recognize these laws popping up in actual sentences. The way you do that generally is by breaking down the sentence, calling parts of sentences that are the same by the same letter, whether it be P or Q or R. Okay, use deductive reasoning to answer the following. State which logical law you are using, state the conclusion that can be made, and if you're not able to make a logical conclusion, then we will instead write no logical conclusion. So, if two segments have the same length, then they are congruent. You know that BC is equal to XY. That's what we're starting with. Okay. Big difference between these two. This one will only start by giving you one if-then statement. This one will give you two. How many if-then statements do you see here? One, which means it's definitely not the law of syllogism. If anything, it's the law of detachment. So, this is the hypothesis of the original one. That's P. This is the conclusion of that if-then statement. That's Q. So this first sentence is fitting this first bullet point. To make a logical conclusion, the other sentence has to say something that indicates that P is true. This sentence right here has to say some version of two segments have the same length. It does. That's a segment, that's a segment. Equal segments means they have the same length. So, this is a version of saying P is true. And since it fits this format, we can use law of detachment to make a conclusion. If it doesn't fit either law of detachment or law of syllogism setups, then you can't make a logical conclusion. This one does. It fits under law of detachment. So now we make the conclusion. The original conclusion said they are congruent. The P that it gave me in the second part is talking about B, C, and X, Y. So our conclusion would be that B, C, and X, Y are congruent. Remember, when you're writing that segments are congruent, you do put the bar above them, and the congruent symbol looks like an equal sign with the squiggle. Okay, so I don't have to keep scrolling. I'm going to write this on the board. Detachment. If P, then Q. P. Therefore, we conclude Q. And syllogism. If P, then Q. If Q, then R. And we conclude If P then R. Okay. If you are studying botany, then you are studying science. If you are studying science, then you are a scientist. How many if-then statements do you see? 2, which means if it fits either of them, it is going to be syllogism. Hypothesis and a conclusion. A hypothesis and its conclusion. First one, I'm going to mark P and Q. The second one, since it uses the same letter in the law of syllogism in 2 places, I have to make sure they match. Does this match this?
Yeah.
You are studying science, you are studying science. Yeah, those match, which means that is Q. Leading to this being R. If P, then Q. If Q, then R. That's what this says. So that is law of syllogism. Law of syllogism's conclusion is an if-then statement. So if, specifically it says P. According to this, we said P was? You are studying botany. Then, it concludes with R. R, we said, is? You are a scientist. So that's the process that we're essentially going to go through here. Look at how many conditional statements they are. See if it matches up with one of these setups. If so, make a conclusion and say which law. If not, say no logical conclusion. Okay, if R is less than the measure, if 90 degrees is less than the measure of angle R, which is less than 180 degrees, then angle R is obtuse. Angle R is an obtuse angle. Okay? How many if-then statements? 1, which means we're looking for law of detachment. That's P. That's Q. Fits the first piece. The second piece, the second sentence has to be P. Does that match P? That matches Q. It says angle R is obtuse, which means it doesn't fit one of our 2 laws, and so we say that there is no logical conclusion. Same idea, but I didn't ask you to solve, which is what no solution means. D. If x is greater than 5, then x squared is greater than 25. If x squared is greater than 20, then x squared is greater than 25. How many if-thens? 2, which means we're looking at law of syllogism. Now, I'm going to give you a quick warning. Law of syllogism, sometimes they're backwards on which if-then goes first. The key thing you're looking for with law of syllogism is one of the hypotheses needs to match the other one's conclusion. So, that's a hypothesis, that's a conclusion. That's a hypothesis, that's a conclusion. Do we have any matching? X squared is greater than 25 shows up twice. But do you notice that they're both conclusions? Should they both be conclusions? No, one a hypothesis, one a conclusion. Which means if the conclusions are the ones that match, it doesn't fit law of syllogism. Two if-thens means it doesn't fit law of detachment, which means no logical conclusion. I believe we have some more examples on the back, but then we're done with notes today. It's just these examples. Law of detachment and law of syllogism, because of some of the quirks of it, messes with people. That's why we're going to go through more examples than we typically would. Okay. If you get an A on your math test, then you could go to the movies. My favorite actor is James Earl Jones. Nothing matches, does it? So, it is one conditional statement, so I think law of detachment, but this doesn't have anything to do with that if-then statement. And if there's no matching whatsoever, that's an easy no logical conclusion. Liking James Earl Jones tells you nothing about how you did on the math test, or if you can go to the movies. If it does not rain, then I will walk to school. If I walk to school, then I will wear my sneakers. Number of if-thens? 2, making me think of law of syllogism. Okay. Hypothesis, conclusion. Hypothesis, conclusion. Do I have matching? Yes, where do they match? What statement? I will walk to school. One's a hypothesis, one's a conclusion. Is that good?
Yeah.
Yep. Now the matching ones are the cues. P is the other hypothesis. R is the other conclusion. P, Q, Q, R does fit law of syllogism. The conclusion is where people get stuck, if they get stuck on these laws. Has to do with the fact that they are different between the two of them. Detachment is a single statement. Syllogism is an if-then statement. If. What? It doesn't rain. Then, Nate was correct. I will wear my sneakers. If a triangle has equal side lengths, then each interior angle measures 60 degrees. Triangle ABC has equal side lengths. How many of them? One. Makes me think of which law? Detachment. That's the hypothesis. That's the conclusion, which means that's the P. That's the Q. Which one does this need to match on detachment? P. P says a triangle has equal side lengths. Triangle ABC has equal side lengths. Is it matching? Yeah, it's getting more specific. Law of detachment gets more specific and says a specific item does this, but it does match. It's saying equal side lengths on a triangle. So, that is law of detachment. And our conclusion is, according to this, I conclude Q. Now I get more specific in the same way that P got more specific. Between these, it got more specific, and instead of saying a triangle, it gave the triangle's name. So in my conclusion, I give the triangle's name. Now, you haven't seen this notation yet. We will get to this notation, but when you name a triangle, you actually put a triangle symbol in front of it, and then it's 3 capital letters. It's the reason why when we name planes and when we name angles, we have to have either the word plane or the angle symbol in front of them, because 3 letters names a lot of things. Triangle ABC has 60-degree interior angles. Final example says if x is greater than 1, then 3x is greater than 3. If 3 squared is greater than x, then 3x is greater than 1. Nothing matches. If nothing matches, that's automatically no logical conclusion. Got a worksheet for y'all today. No, we've been doing a lot with book assignments, but we are moving into a worksheet today. Does this show up on there? Yeah. 2.2. Today is the 26th. It's Thursday the 26th, which means our homework's due on Monday, which is the 30th, and it's the 2.2 worksheet.